So now on to the deep dive. In this episode, we're going to be talking about the greenhouse effect. So in the last episode, I talked about orbital forcing and how that controls climate changes on timescales of thousands of years. And the next obvious thing to talk about would be greenhouse gases. But first, I need to do an overview on what exactly is the greenhouse effect and why greenhouse gases are important on climate. The first thing to note is that without the greenhouse effect, the surface of the Earth would be a lot colder. And in fact, it would probably be too cold for liquid water to exist in most places. And without liquid water, life cannot exist. So it would just be too cold. So to understand what the greenhouse effect is and why greenhouse gases warm the planet, the first concept we need to think about is electromagnetic radiation. So, what is electromagnetic radiation? It can be best thought of as a way to transfer energy through space. And yeah, it basically acts as sort of a wave, so it oscillates. And in a vacuum, electromagnetic radiation travels at the speed of light, which is about 300 million meters per second. And basically, there are differences in the wavelength. So basically, how far each oscillation goes, and you can measure the wavelength. Say for visible light, there's like red light has a longer wavelength than blue light, and you can measure this pretty easily using a variety of techniques. If you take university physics, you can find out more. But the important thing is that how electromagnetic radiation interacts with matter is dependent on the wavelength of the radiation. The second concept is molecules. So everything that has basically all matter is made up with molecules. And molecules are made up of individual atoms, so two or more atoms. So the important thing with relation to how electromagnetic waves interact with molecules is based on the electrical charge of the molecule, and specifically how it's distributed within a molecule. So, as I said, the molecules are made of several atoms, and atoms have a nucleus which contains most of the mass of the atom. The atoms have protons and neutrons, and each proton has a positive charge. And then surrounding the nucleus are these electrons, which have a negative charge. And the electrons don't really have much mass, but they basically, in most simple models of an atom, they sort of orbit around the nucleus. And basically, the properties of each atom is dependent on the number of protons and electrons. So how different atoms will bond together to make a molecule is dependent on the properties of the atom based on how many protons, electrons it has. And basically, the distribution in a molecule, the distribution of where the charge is, will depend on the different atoms that make up the molecule. As an example, for water, there's one atom of oxygen and two atoms of hydrogen, and they form a bond that sort of makes it look like a triangular shape. So because the charge distribution will pull the electrons of the oxygen atom towards the hydrogen atoms in the bond, the peak of that triangular part where the oxygen atom is will have more positive charge relative to the bars that connect the hydrogen and oxygen atoms. So there'll be more positive charge in the different sides of the molecule, and that will affect how electromagnetic radiation will interact with the molecule. So, so basically, if for complicated molecules that are made up of more than one type of atom, it is much more likely that electromagnetic radiation can interact with the molecule, so basically colliding with it. Whereas the basically singular atoms or atoms with or molecules with just two of the same atom are less likely to interact with electromagnetic radiation, because the distribution of electrical charge within the molecule is more distributed more evenly. And basically, whenever the electromagnetic radiation, whenever it hits the molecule, it will basically transfer the energy from the radiation into the molecule, and it causes the atoms in the molecule to vibrate. And as it's vibrating, it will again release the energy that was gained from the initial interaction with the electromagnetic radiation, but the wavelength of the radiation that comes out will be at a longer wavelength. And basically, all the molecules want to eventually stop vibrating, and the vigor of the vibration is what gives matter its heat. So that's essentially what heat is. If the molecules are not vibrating, that means the temperature is as close to absolute zero, and anything that has a temperature above absolute zero will have the molecules vibrating, and they'll be emitting long wavelength electromagnetic radiation. So yeah, basically, the hotter something is and the more vigorous the molecules are vibrating, the shorter the wavelength of the radiation that is emitted. And yeah, basically, the more complicated a molecule is, the more likely that there will be these interactions with electromagnetic radiation. So yeah, the next topic will be on shortwave and long-wave radiation, and this is basically a definition based on the wavelength of the radiation. So yeah, the surface of the sun is really hot. So the sun, generally speaking, is emitting a lot of shortwave radiation, and it has wavelengths between about 100 nanometers and 1500 nanometers or so. And basically that means it's this band of radiation is what's heating up the Earth. However, the surface of the Earth is comparatively cold, so most of the radiation that is emitted from the Earth is long wave radiation, and if you look at the wavelengths of the radiation emitted from the sun and the wavelengths radiated from the Earth, there's almost no overlap in the wavelength of the radiation between these two bodies. And this is important when we are thinking about the greenhouse effect. So yeah, the short wavelength radiation, a lot of that is able to penetrate through the atmosphere, and we can see that that's a lot of it is visible light. Like our eyes have evolved to be able to see the kind of radiation that is able to penetrate through the atmosphere. So, in terms of how the atmosphere absorbs radiation, the the sun's radiation, which is above 100 nanometers, most of that energy is able to penetrate through the atmosphere, which is, say, the gases that make up the Earth's atmosphere are transparent to the radiation coming from the sun. A lot of the outgoing radiation is also able to penetrate through the atmosphere. So basically, you'll have some energy from electromagnetic radiation coming through the atmosphere. It hits the ground. It warms up the surface of the Earth because the Earth's surface, the ground can absorb a lot of the radiation that's coming from the sun, and that warms up the surface, and that energy is released as long wave radiation, which also can escape most of it through the atmosphere. And the key point is that if the Earth's surface temperature is constant, that means that there has to be a balance between the energy that is being absorbed from sunlight and the amount of energy that's lost through this long wavelength radiation. So, what is the atmosphere made up? The Earth's atmosphere is made up of about 78% nitrogen gas, 20.95% oxygen gas, and 0.93% argon. And basically any other gas is basically just a trace amount in the atmosphere. The largest concentration of a trace molecule, trace gas in the atmosphere is carbon dioxide. And that only makes up about, as of 2024, about 0.0424% of the gas in the atmosphere. So it's far less than even argon, which is the third largest constituent of the atmosphere. When I'm talking about that, I exclude water because the amount of water in the atmosphere varies with time. If there's too much water, it will rain. So the amount of water in the air can vary between 0% in a desert area to as high as 4% in a very humid tropical area. So we'll keep that in mind in the next few slides. So when we talk about absorption, most of the atmosphere is made of nitrogen, oxygen, and argon gases. And basically, nitrogen gas, which is two nitrogen atoms in a molecule, and argon, which is just an argon atom, they absorb almost no radiation in the wavelength bands that are emitted by the sun and the Earth. So those two atoms are not important in terms of the greenhouse effect. They don't really affect anything at all. The the radiation just goes through it without interacting with these atoms. Oxygen, even though it's two, there's two different molecules of oxygen in the atmosphere. One is with 2 oxygen atoms, and one with 3. And the one with 3 is known as ozone. Oxygen, dioxygen, the oxygen gas with 2 atoms, does interact a bit with the radiation that is relevant to the greenhouse effect, but it's only a very small amount. And ozone has a bigger effect, but it's only really found in the upper atmosphere. It reacts very quickly chemically with other when it's closer to the Earth's surface. So ozone is a very strong greenhouse gas, and it's mostly relevant though at the very short wavelengths, like in the ultraviolet range. And that's why the destruction of the ozone layer is so bad, because if you get rid of the ozone, then ultraviolet radiation is able to penetrate through the atmosphere, and that can cause skin cancer. And yeah, basically, if the Earth's atmosphere was only composed of these 3 different gases, most of the radiation could go in and out very easily. But of course, there's these other molecules that are more complicated than, oxygen and nitrogen and argon, and that includes carbon dioxide. However, the main greenhouse gas is actually water. So water is able to absorb radiation at a very large range of wavelengths, and you can notice that very easily when you compare a day when it's humid versus a day where it's dry out. If it's sunny out, a day that is humid is going to feel a lot hotter, and that's because of this greenhouse effect. The water in the atmosphere is absorbing more long wavelength radiation, and carbon dioxide is very important because it absorbs a lot of the outgoing radiation at wavelengths of about 10 micrometers. And that's important because water doesn't absorb much radiation at this 10 micrometers band. So as you increase carbon dioxide, it will basically absorb more energy in this band that water's not in. So some people say, oh yeah, water is an important greenhouse gas, and we don't talk about that in climate change, and that's because the atmosphere can only hold so much water, and it varies with time, whereas carbon dioxide, once you put it in the atmosphere, it doesn't come out very easily, and it's absorbing radiation basically at the peak of the long wavelength radiation that is emitted from the Earth. And yeah, basically, as the carbon dioxide is vibrating, and it's emitting more long wave radiation that goes back down to the Earth, and that's absorbed by the Earth's surface, and that's why you have this greenhouse effect. And it's not just carbon dioxide. There's also nitrous oxide, and there's also methane, and those 2 gases are actually more powerful greenhouse gases, but there's a lot less of those molecules in the atmosphere. And especially with methane, the methane is not very stable in the atmosphere. It will tend to have chemical reactions and break down in a few years. So Carbon dioxide is a much more stable molecule. It doesn't tend to be removed from the atmosphere very quickly. And yeah, without the greenhouse effect from these greenhouse gases, the Earth's surface would be a lot colder. So it is important as a way to keep the Earth livable. But yeah, in the next episode, I will talk more about the role of carbon dioxide in regulating climate changes over longer periods of time. All right, that's the deep dive.